and welcome to session 4 of Unit 3. This session would introduce you to the nucleon stability in nuclear chemistry. By the end of this session, you should be able to explain nucleon stability. We shall begin by looking at nuclear stability. Nuclear stability can be thought of as the amount of time that the nuclide will exist as an isotope without undergoing any sort of decay. So the higher the amount of time it can stay, the more stable it is. Now the key factor that helps us to determine whether a nuclide is stable or not is the ratio of its neutron to proton. So for lighter nuclides, if the neutron to proton ratio is 1, then it means that that nuclide is stable or has higher stability. But for heavier nuclides, we can determine its stability by the number of neutrons. The number of neutrons must exceed the number of protons. Once the number of neutrons exceeds the number of protons, then that nuclide is said to be stable. Also, if the number of neutron to proton ratio is too high or too low, the nuclide will be unstable and it will decay. There are some general deductions that we can make concerning the stability of a nuclide, and one of them is that the minimum N to Z ratio for stability is 1. There are, however, two exceptions, which is the hydrogen and then the helium-3 isotope, where the helium-3 isotope has a neutron to proton ratio less than 1. For lighter stable nuclides, the neutron to proton ratio is approximately 1. Example, the helium, carbon 12, oxygen 16, and neon. Also, another general deduction we can make is that the N to Z ratio increases gradually as the atomic number increases, and the ratio can increase from 1 to not more than 1.5. We can also say that all nuclides with atomic number greater than 83 are unstable, regardless of their N to Z ratio. So we can conclude that group 1A, 2A, 6A, 7A, and 8A elements are all radioactive, and they are the actinides and the elements in the 4th transition series, period 7. Bismuth is the heaviest stable nuclide, and it has N to Z value of 1.52. Have you been wondering, given that the protons are positively charged and the neutrons have no charge, what exactly holds the nucleus together? We know that positive charges may never want to be close to each other. We shall get an answer to this as we go on. In the nucleus, there is always repulsion between the positively charged protons and the nucleus, and so it's assumed that this repulsion should rip off the nucleus apart. However, it doesn't happen that way. The reason to this is that there is also an attractive force that holds the protons and the neutrons together in the nucleus. This attractive force is about 100 times stronger than the repulsive force that exists between the protons and the protons in the nucleus, and so this strong force holds the nucleus together and prevents it from ripping off. So in conclusion, what we are saying is that even though there is repulsive force between the individual protons found in the nucleus because they are of the same charge, the nucleus is not destroyed, it's not ripped off, or it's not ripped apart, because there is also an attractive force that holds the protons and the neutrons together. This attractive force is stronger than the repulsive force between the protons and the neutrons, so it keeps the nucleus together. To relate these to nuclear stability, it is the competition between the repulsive force and the attractive force that ultimately determines the stability of the nucleus. When we study the stability of nuclides, there are two interesting points that appear. One of them is that elements with an even number of protons, that is, they have Z to be even. Even numbers include 2, 4, 6, 8, 10, and so on, usually have a large number of stable nuclei, or they are able to form many isotopes with stable many isotopes that are stable than elements with odd number of protons. Interestingly, the oddness of or evenness of the neutrons and protons in the nucleus is related to some important patterns of nuclear stability, which we'll be looking at in our following slides. Many elements on the periodic table have the property of gradually changing their mass number due to change in their neutron number, and this new form that they assume is referred to as an isotope of the original one, or a nuclide. Several elements can form different kinds of nuclides, but not all the nuclides that are formed will be stable. We shall look at elements number 48 to 54 on the periodic table, the number of nuclides they form and number of stable nuclides they can form. So the table below shows elements from 48 to 54 on the periodic table, starting from cadmium to xenon, and you realized from the table that cadmium has an atomic number of 48, and 8 of its nuclei or isotopes that it forms are stable, and the same thing is done for the remaining elements through to xenon Xe, which has 54 atomic number or number of protons, and 9 of its isotopes or nuclei that it forms are stable. More than half of all the stable nuclei that are known have both their proton number and neutron numbers to be even. There are also 7 isotopes that are known with odd neutron and odd proton number. They include the hydrogen, lithium, beryllium, boron, nitrogen is also there, vanadium is there, and some other ones too. Now, the vanadium, lanthanum, and lutetium, the Lu, they decayed slowly and very slowly, to the extent that their amount changed only very little since the Earth was formed. The table on this page represents an even to odd classification of stable nuclides. Now, there are 154 nuclides that have their atomic numbers even and their neutron numbers also even. There are 53 isotopes that are known, or stable isotopes that are known, with their atomic number even and neutron number odd. There are also 50 stable nuclides or isotopes that are known with odd proton number and even neutron number, and only 7 stable isotopes are known with odd proton number and odd neutron number. So a total of 267 stable nuclides are known. Now there is a model that tries to explain this observation where even proton number, even neutron number should give a stable nuclide, or even odd should give a stable nuclide. And this model made a theory that the protons and neutrons in a particular atom lie in shells or in nucleon shells or in energy levels, and their stability is derived from the fact that there is pairing of the nucleons. This arrangement leads to the stability of even numbers of species, and because of that, all the species are paired. We shall be looking at magic numbers as pertaining to nuclear stability. The octet rule was formulated from the observation that atoms with 8 valence electrons were especially stable. A similar situation applies to nuclei regarding the number of neutrons and protons that generate stable isotope. These magic numbers are natural occurrences in isotopes that are particularly stable. When there is an atom that has a proton number of 2, 8, 20, 28, 50, 82, and 114, or neutron number of 2, 8, 20, 28, 50, 82, 126, and 118. These numbers usually account for stability, and so these numbers are referred to as magic numbers because their presence makes the nuclei stable. Stable nuclides or isotopes, they have either their protons or their neutrons possessing these magic numbers. However, when both the proton and the neutron number is a magic number, then it is referred to as double magic number. It is also very good for us to know that isotopes consisting of combination of even to even, even to odd, odd to even, and odd to odd are all stable. We are referring to proton to neutron number. There are also more nuclides that have a combination of even to even than odd to odd, and we can see that in our previous slide. From what we have learned so far, we can deduce that there are two main factors that determine nuclear stability, and they are the neutron to proton ratio, that is N to P ratio, and also the total number of nucleons in the nucleus. The principal factor for determining the stability of a nucleus is the neutron to proton ratio. So elements with proton number of less than 20 are referred to as lighter elements, and their neutron to proton ratio is always 1:1, and that means that they are stable nuclides. They mostly prefer to have the same number of neutrons as protons. However, elements with atomic number 20 to 83, they are known as heavier elements, and their neutron to proton ratio is 1.5:1, which makes them unstable. Now, it means that the neutron is 1.5 as against 1, in terms of ratio. Now these values could be a very huge value, let's say 30 against 20. So 30 neutrons, 20 protons, and when you simplify, you break it down, you get it as 1.5 is to 1. The reason for this difference in neutron to proton ratio is because of the repulsive force between the protons. So the stronger the repulsive force, the more neutrons are needed to stabilize the nucleus. So these nuclei that are having stronger repulsive forces between the nucleon, that's the protons, within the protons, more neutrons are needed to neutralize it or neutralize the repulsive force. So they will end up having more neutrons than protons. An example is illustrated with the carbon 12, where there are 6 protons and 12 atomic mass, which can help us to calculate the number of neutrons, and that will give us neutron number of 6 to 6 also. In that case, the ratio of neutron to proton is 6 is to 6, which we can break it down to 1 is to 1. This is a stable ratio, and it lies in the belt of stability. We shall be looking at the belt of stability as we proceed in this course. These are self-assessment questions which I will leave you to them, and I would want you to go through them to get yourselves more familiar with the course.